Hi everyone, today we are getting our hands dirty with Python's memory management. We are going to break circular references, visualize memory leaks, and learn real-world cleanup strategies. Let's jump right in. Alright, let's pull back the curtain on Python's memory management. First, let's actually see reference counting in action. This is like watching memory traffic in real time. We start simple. We create a list and assign it to my object. Look at that reference count badge. It says 1. That makes sense, right? One variable, one reference. Python's keeping track. But here is where it gets interesting. We are also creating a ref count visualizer object to help us peek under the hood. And that's where things start to multiply. Watch what happens when we create that visualizer. Inside the init method, we do self-object equals to object, right? Bam! The reference count jumps to 2. Why? Because now two things point to our list. The original myObject variable and this self-object instance variable. See those arrows? Each arrow is like a librarian's checkout card. Python tracks them all. Now comes the tricky part. When we call the show method, look at the reference count. It's 3, but we only created 2 references, right? Here is the sneaky bit. If you remember, sysgetRefCount itself creates a temporary reference. When you pass an object to any function, including getRefCount, Python creates a parameter reference. So now we have first my object, our original one, self-object, the instance variable, and the third, the parameter to sysgetRefCount, the temporary one. Python's like a super cautious librarian. Even checking out the book to count how many times it's checked out counts as checking it out. And this is why we subtract 2. Look at the code, sysgetRefCount, self-object minus 2. We are subtracting 1 for self-object, our measurements tool, our own reference, and another one for getRefCount parameter, the act of measuring. It's like, imagine you are counting people in a room, but you are in the room and you bought a mirror. You gotta subtract yourself and your reflection to get the real count. So getRefCount returns 3, we subtract 2, and we get 1, the real number of references we care about. Okay, now let's add another reference. Ref1 equals to myObject. Watch the counter jump to 2. See the new arrow pointing down. That's ref1. Now 4 things total reference our list. myObject, self-object, sysgetRefCount, and the new one, ref1. 4 references minus the 2 hidden ones equals 2 visible references. Python's counting everything. Let's add another. Ref2 equals to myObject. The counter goes to 3. Each assignment with the equal operator, that's another checkout card. 5 total references now, minus the 2 hidden ones. See how every arrow represents a real connection in memory. This is happening constantly in your Python program. You just never see it, but Python's internal librarian, we are working overtime. Now watch this. We create a list and add our objects there twice. The count jumps to 5. Why? Because each element in a container is its own reference. Look at those arrows, container 0 and container 1. They are both pointing at the same object. One list, but 2 references. This is why passing objects around in Python is so efficient. You are not copying the data. You are just adding another arrow, another checkout card. The actual list exists once in memory. Let's clean up. We are gonna delete the reference 1. Watch the counter drop to 4. See that? 1 arrow disappears. That's Python's garbage collector at work. Well, technically the reference counter is part of the garbage collector. When we delete something, Python decrements the counter. Simple, elegant, automatic. Finally, let's delete the container. The count drops to 2. Notice it drops by 2. That's because the container had 2 references, one for each element. Each arrow that vanishes in Python saying, okay, one less checkout card for this book. And when the counter hits 0, that's when the actual object gets cleaned up. Memory gets freed. The book goes back on the shelf, or in this case, gets recycled entirely. So there you have it, reference counting in action. Every equal sign, every list element, every function parameter, they all increment the counter. Python's like a meticulous librarian, keeping track of every single book checkout. And that -2 in the code, that's us being honest about overhead of measurement itself. We are subtracting our own footprint to see the real picture. This is happening millions of times per second in your Python programs. And it's one of the reasons Python just works. You never have to think about memory management because this elegant system handles it all automatically. Alright, now things get spicy. We have seen how reference counting works beautifully, but there is a fatal flaw. Let me show you the classic memory leak, circular references. We already talked about that in kind of theory way. It's like two friends who never leave the party because each one is waiting for the other to leave first. Spoiler alert, they are both stuck there forever. Let's start simple. We create a best friends object named Alice. Look at that reference count. It's 1. One variable pointing to Alice. Everything is normal. See the arrow from the Alice variable pointing up? That's our single reference. Python's happy, we are happy, Alice is happy. Now we create Bob, another best friends object. His reference count is also 1. 2 separate objects, 2 separate variables, everything is still perfectly normal. At this point, these are just 2 independent objects living their best lives in memory. No connection between them yet. Now watch this. We set Alice's bestie to be Bob. Look what happens to Bob's reference count. It jumps to 2. Why? Because now 2 things point to Bob. The Bob variable, Alice's bestie attribute. See that curved arrow going from Alice to Bob? That's the new reference. Still perfectly legal, still totally fine. Python's reference counting is handling this beautifully. Here comes the problem. We do Bob bestie equals to Alice. Bam! Now look at the visualization. See those 2 curved arrows? They form a circle. Alice points to Bob, Bob points to Alice, and check out those reference counts. Both are 2 now. For Alice, the Alice variable, Bob's bestie attribute pointing back. For Bob, the Bob variable, Alice's bestie attribute pointing back. This looks fine, right? Reference counting says both objects have 2 references. Everything seems normal, but we just created a time bomb. Now let's clean up. We do del Alice and del Bob. Watch what happens. The variables disappear. See how they are crossed out and faded? But look at the objects themselves. They are still there. The reference counts drop to 1 each, but they are not 0. Here's a nightmare scenario. Alice's reference count is 1 from Bob's bestie. Bob's reference count is 1 from Alice's bestie. They are keeping each other alive. It's like 2 people holding hands in a locked room. Neither can leave because they are holding onto each other. Look at this. The variable Alice and Bob are gone. We deleted them. They are out of scope, but the actual object still sitting in memory. This is the fundamental limitation of reference counting. Python's simple count the arrows approach can't detect cycles. As long as those circle arrows exist, the reference counts will never hit 0. The objects are completely unreachable from our code. We can't even access them anymore, but they are stuck in memory limbo, taking up space forever. Reference counting alone can't solve this. The objects are stuck in memory limbo forever unless we call garbage collect. The garbage collector, and watch what happens. Finally, both objects disappear in that fade out animation. The del methods fire, printing those finally deleted messages. The memory is freed. The garbage collector is smarter than simple reference counting. It can detect cycles. It says, hey, these two objects point to each other, but nobody from the outside world can reach them. They are garbage. And proof, it breaks the cycle and cleans them up. But here's the thing. You usually don't want to wait for the garbage collector to run for this. It's unpredictable. It has overhead, and in some cases, it might not run at all. So how do we solve this? How do we write code that doesn't create these circular references nightmares in the first place? There are 3 elegant solutions. I'm about to show you all of them. Solution number 1, the breakup method. Sometimes you just gotta manually break the cycle. It's brutal but effective. Here we go again. Alice and Bob are best friends. They point to each other. Both have ref counts of 2. We have seen this trap before. Those circular arrows, that's our problem waiting to happen. Now watch. We set Alice's bestie to none. It's like saying, it's not you, it's me. Look what happens to Bob's ref count. Drops to 1. The arrow from Alice to Bob disappears. We just severed one side of the circle. Bob still points back to Alice though. See that remaining arrow? He hasn't gotten the memo yet. Now we complete the breakup by setting Bob bestie to none. Clean break. Both arrows vanish. Both ref counts are 1. The cycle is broken. No more circular references. Just 2 independent objects with 1 reference each. And here is a payoff. We do del Alice and del Bob, and bam! Both del methods fire instantly. See those objects fade out? That's immediate cleanup. No waiting for garbage collection, no memory leak, just clean, predictable destruction. This is method 1. If you control the life cycle, manually break the links before cleanup. Simple, explicit, 0 overhead. But manually setting things to none? That's tedious. What if there is a better way? And for that, let's look at the method 2, weak references, which is Python built-in module. And of course, we're going to import that. It's going to be the elegant solution. This is like having a friendship that doesn't create attachment issues. First, look at the code. See that we graph friend. That's the magic. We create Charlie and Diana, then set them as each other's besties. But notice those dash lighter arrows? Those represent weak references. Here is the brilliant part. Weak references don't increase the ref count. Both Charlie and Diana have a ref count of 1 just from their variable names. The bestie connections, they are invisible to the reference counter. It's like saying, I know you exist, but I'm not holding on to you for dear life. Let me explain the property getter setter real quick because it's doing something clever. When you access charlie.bestie, this getter is called. It checks if the weak reference exists, then calls it with parentheses to get the actual object back. Weak refs are like phone numbers. You gotta dial them to reach the person. When you set Charlie the best equals to Diana, this setter wraps Diana in a weak reference. We are storing a reference that Python's counter ignores. Let's verify cscatter count, which shows both have a ref count of 1. Think about that. They point to each other, but the ref counts are 1 with normal references. This would be 2. That's the power of weak refs. They don't count. Now watch. We're gonna delete Charlie and bam, his del fires immediately. See? Charlie fade out. No circular reference problem. His ref count was 1. We deleted the only real reference, so he is gone instantly. Diana's reference to Charlie, it automatically becomes none. Python handles that for us. The weak ref realizes, oh, the thing I was pointing to is gone, and cleans itself up. Let's delete Diana. She's gone too. Instant cleanup, no garbage collector needed. Both objects destroyed immediately. No cycles, no leaks, no waiting. This is how you design relationships that don't create dependencies. Yeah, so weak references are perfect for things like observer patterns. Listeners shouldn't keep the subject alive. Caches, you want entries that can disappear when memory is tight. Parent-child relationships, where the child shouldn't prevent parent cleanup. It's saying, I want to know about you, but I won't prevent you from leaving when it's your time. But what if your circular references are more complex, like a whole graph of interconnected nodes? That's where method 3 comes in. And finally, method 3, context managers, the professional solution. This is how you handle complex hierarchies with circular references like organizational charts, project graphs, or team structures. Before we animate this, let's understand what we are building. Look at the code. We have got an employee class. That's simple. Just a name, a manager reference. Sorry about that. A manager reference and a team list. Nothing fancy. But then we have the team cache class. This is our context manager, and context managers have 2 special methods, as you may know. The enter method. This runs when you enter the with block. Look at what it does. Creates all 5 employees, builds the CEO's team by setting references both ways, and builds each manager's team the same way, circular references everywhere. Stores everything in self-employees, this is our cleanup list, returns the team so you can use it. Very confusing, huh? And exit method. This runs automatically when you leave the with block. It's the cleanup crew. Loops through every employee, sets manager to be none, which breaks upward references, clears the theme list, which breaks downward references, and clears the master list, so memory is now free to be reclaimed. It's like building a house of cards inside a protective box. The with statement is that box. When you step outside, the context manager carefully dismantles every card before you walk away. Now let's watch it in action. Watch this animation. We are creating 5 employee objects, one by one. Sarah, the CEO, 2 managers, Mike and Lisa, and 2 developers, John and Emma. See them pop up into existence? Right now, they are just independent objects, no connections yet. Each has a ref count of 1 just from their variable names. This is the setup phase inside enter method, the context manager's initialization method. Now we build the first layer of circular references. Look at those arrows shooting out. Sarah's team list gets Mike and Lisa. That's two references going down, but then see the arrows coming back up. Mike and Lisa both set manager to be equal to CEO. That's the circle. Mike now has a rev count of 5 because the manager 1 variable itself. He's in Sarah's team in the 0 index. He's gonna be in his own team list, and his 2 developers will reference him back. See how quickly this gets complex. This is why we need a strategy. Now Mike builds his team. He gets John and Emma. More arrows going down. Team 0 and Team 1. And more arrows coming back up. Both developers set manager to be manager 1. Look at all those reference count badges lighting up. Everyone's interconnected now. This is a maze of circular references. Sarah references her managers, managers reference Sarah back, Mike represents his developers, developers reference Mike back. Whew, a lot. Traditional reference counting can't handle this. When we try to delete, nothing will happen because everyone's keeping everyone else alive. Here is the complete picture. Look at those actual reference counts. Well, you can read it on your own already. Let me just skip this part. This is exactly the kind of structure that would cause a memory leak with naive reference counting. And now we use it. Look at that inside with block context box. We can access the CEO, see her reports, traverse the entire hierarchy. The circle references exist. They are working exactly as intended for our business logic. Sarah knows her managers, managers know their CEO. It's a functional organizational chart. But here is the genius part. The context manager is keeping track of all these objects in self-employees list. It's like having a master cleanup list. And this is where the magic happens. When we exit the with block, exit method fires automatically. Watch what it does. It loops through every employee and systematically breaks the references. First, we set manager attribute to be none and set team attribute to be an empty list. And that cleanup visualization, we are severing every single arrow, breaking every cycle. Then we clear the employee list. And boom! Memory can now be freed. All those reference counts drop to 0. Everything gets cleaned up immediately. No garbage collector needed. And this is the power of context managers for complex structures. It's explicit, it's reliable, and it's how professionals handle complex objects graphs in Python. The context manager is saying, I know you are going to create a mass of circular references. That's fine. I'll keep track of everything and clean it up when we are done. It's like having a responsible adult supervising the chaos. So, there you have it. 3 solutions. Manual cleanup, simple, explicit, but tedious. Big references, elegance for specific patterns, but requires careful design. And context managers, professional grade for complex hierarchies. Pick the right tool for the job and you'll never leak memory again. And that's how you master Python memory management. You have learned to spy on reference counts, break circular references, and write leak-proof code. Remember, Python manages memory for you, but you manage the relationships between objects. Before we wrap up, let me show you one more powerful tool, Memory Profiler. This lets you see exactly how much memory each line of your code uses. Perfect for finding those memory leaks we have been talking about. First, install it. pip install memory profiler. Then just add the add profile decorator to any function you want to monitor. That's it. Add the decorator and call your function. It can be just any function for now. Now run your script with python-m memory profiler, whatever your Python file name is. Look at this output. We got 5 columns. First, line number, where in your code. Second, mem usage, total memory at that point. This is the most important. Then comes increments, sometimes shows weird negative values. Ignore those. Occurrences, how many times the line ran. And the last one is just to see your line contents. The key is comparing mem usage value. As we see, it started with 35.4 megabytes and then jumped to 73 megabytes. That's 37.6 megabytes increase for our list. Line 7 and line 8 stayed at 73 megabytes. No extra memory needed. Here it is visualized. You can see exactly where the memory jumps from 35.4 to 73 megabytes. This is your memory hotspot. This is incredibly useful when debugging memory leaks or circular references like we talked about today. So there you have it. In 2 simple steps, you can profile any Python function and see exactly where memory is being used. Add this to your debugging toolkit. See you next time. I hope this video was useful for you. You can like and subscribe. And thanks for watching.